Hello everyone, and welcome back to my YouTube channel, AlexAeroLab, where I go over my very own motorsport aero projects. Alright, in my last video I went over who I am and what this channel is going to be about, and I've linked that video in the description, so please check that out. But I didn't really go into what type of content to expect on this channel. Motorsport aero is a huge field. You can approach it experimentally or computationally, and has percolated through all motorsports, from students to the very pinnacle of every discipline, on and off track. So how to tackle such a big field? Well, I'm gonna break down the content of this channel into a bunch of series, with each series comprising of its own mini projects. These projects are gonna start simple and then build in complexity until by the very end of each series, I hope to be able to do some of my very own design work. I'm gonna try to upload a new video every week. These videos are gonna look sort of like this one, which is an introductory video. They might look like maybe more of a vlog style progress report, or they'll be longer full-length videos where I'm going to be going into the actual results of each project. So without further ado, let's get into this first series on the aerodynamics of Formula One front wings. Now, to drastically simplify, all aero devices on the car are designed to do more or less two things: generate downforce, thus affecting the normal forces experienced in the tire contact patches, or reduce the drag of the car. By reducing the drag, the car will be able to achieve higher speeds at a given engine output. Or you could also look at this as, at a given speed, the car will use less fuel and energy. The downforce contribution to the tire contact patch normal forces are created by modifying the pressure distribution over and under the car. By having less pressure under the car, a net downforce is achieved, and this force is distributed to the ground at each of the tire contact patches. Increasing this force will generally allow for more grip through the corners and better traction, leading to better lap times. The three main downforce producing devices on modern F1 cars are the rear wing, the underfloor, and the front wing. Now, an F1 car front wing, generally speaking, works like an airplane wing, in the sense that you have airfoil profiles creating a force normal to the free stream flow. However, this is really where that comparison breaks down, because in reality, the F1 front wing is way more complicated and is kind of that wing that your classical aero professor told you not to worry about. Common airplane wings are usually moderate to high aspect ratio, are comprised of a single element, and operate high in the sky far away from the ground. And really one of the main design parameters for them is minimum drag. Race car wings are kind of the opposite in every way. Modern F1 wings are low aspect ratio, multi-element, inverted wings that operate in ground effect. They feature many flow control devices, and with the coming 2026 regulations will feature active aero. Because of these highly viscous effect-dominated flows, many of those classic inviscid methods used to characterize airplane wings do not apply. Additionally, F1 front wings aren't solely designed for maximizing downforce and minimizing drag. They're trim devices. They're used to balance the car as well as redirect flow in relation to the floor and the tires. So with all this in mind, how do we begin this project on the front wing? Well, as I mentioned before, we're going to start simple and build in complexity. So this first project is just going to be a CFD study of a single element wing and ground effect. The goal of the study is to investigate flow features and experimental trends seen for inverted wings and ground effect, as well as to investigate how the type of airfoil changes the performance and behavior of the wing. I'll be performing this study in the open source code OpenFoam. Due to my limited resources, as well as this just being a preliminary study, I will be performing all of my simulations using steady state RANs. The study will vary the wing type, the angle of incident, and the ground clearance to determine downforce, drag, and other flow characteristics. The study will begin with a calibration study, where I select a turbulence model by attempting to replicate some experimental data from Jonathan Zarahan's PhD thesis. In the main study, I will test 5 separate wings. All 5 will be untwisted rectangular planform wings with simple end plates and foot plates. I will select span and chord values based on geometry constraints provided in the 2026 F1 technical regulations. Each wing will differ in the type of airfoil profile used. I know modern F1 teams design their own, but for the scope of this study, I just wanted to see how some predetermined ones would perform. The airfoils I've selected include the NACA 0012, the 4412, the Celic S1223, the Grumman K2, and then the airfoil used as the first element in the 1998 Tyrrell F1 car. I chose the first airfoil, the symmetric airfoil, just to see how it would perform in ground effect. You know, the FIA regulations of the late 2000s and 2010s mandated a symmetric airfoil section of the wing, so just wanted to see how this part affected. The 4412 is just a cambered airfoil. I want to see how that works. I want to see how the high lift S1223 airfoil works. This is an airfoil designed to be high lift into a free stream, and it'll just be interesting to see how it behaves in ground effect. Similarly, I want to see how the K2 airfoil, which is a transonic airfoil, will behave. So for each of these wings, I will run them at 6 angles of incidence and 10 different ride heights, and this will sum in a total of 300 simulations. And all this data is going to provide some great insights how ride height and angle of incidence, as well as the type of airfoil affect the performance, such as lift and drag, as well as the flow field around and behind the wing. So with all that, thank you for watching. Stay tuned as we go through the results of this project. Please like, subscribe, share this video with your friends, and I'll see you in the next few days.